Hey guys, Mr. Betts here. I want to talk about how we can determine using calculus the concavity of a function, and then some other things that we can conclude about a function based on the information that we have. So let's just start with a picture of a graph that we know is concave up. So this is a picture that we've kind of looked at before. It's just a basic parabola. And the concavity essentially tells us which way the curve is curving. So sometimes I like to think of it as like driving along a road, and if we're going from left to right, if we're driving here on this road, we would be turning to the left. That would correspond to concave up. From a calculus perspective, I want to talk about how we could determine this concavity using calculus. So if we think about what calculus can do for us, specifically derivatives, the derivatives are going to tell us the slopes of functions. So the slope of a tangent line at any given point. And if we look at slopes of tangent lines as we move along here, this is just kind of a gross approximation of them. What you might notice is that the slopes start out at a large negative number and become less and less negative until they get to 0. And then the slopes increase to a large positive number. Now, this isn't necessarily going to be what happens every time we have a concave up function. But what is happening here is that if we were to plot the slopes are going to start at a negative number and increase to 0, and then ultimately pass 0 to larger numbers. And so what happens is with a concave up function, the slopes are going to be increasing. And since the slopes are increasing, we're going to say f prime is increasing. This is always going to happen with concave up functions. Then if we want to know when something's increasing, we take the derivative of that and look for where that's positive. Well, the derivative of f prime is f double prime, and we want to know where that's positive. So we've talked about second derivatives before. Now we're actually going to use second derivatives to answer questions about concavity. If a function is concave up, then the second derivative is going to be positive. Now, if we look at the graph of a concave down function, you can see that along this function here, we start with large positive slopes, and the slopes decrease to 0, and then we get large negative slopes. So as we go left to right, or if we think of it as driving down a road, we would be turning to the right. The concave down function is going to be where the derivative is decreasing, the slopes are decreasing, and therefore the derivative of the derivative is going to be negative. So we can use the second derivative and the sign of the second derivative, sign being positive or negative, to determine whether a function is concave up or concave down. So there are really a couple of different things that we could look at if we want to determine concavity. The first is the second derivative. This is usually the way that we'll think of it first. If the second derivative is positive, that's the same thing as saying that the first derivative is increasing. Then we have a function that's going to be concave up. So the graph of the function is going to be concave up. If the second derivative is negative, which is the same thing as saying that the first derivative is decreasing, then the graph of the function is going to be concave down. So just organizing that in a different way, we want to make sure that we're using clear language. So when we're talking about the function, we're going to use concavity. If we're talking about the first derivative, we're going to say increasing or decreasing. And then when we talk about the second derivative, we're going to say positive or negative. All right, and these are all phrasings that we can use to talk about concavity. So a function concave up is the same thing as the function's derivative increasing, and that's the same thing as the function's second derivative positive. And then on the other hand, we have a concave down function is the same thing as a function's derivative decreasing, and that function's second derivative negative. We're also going to talk about something called a point of inflection. And a point of inflection is a point on the graph. And this word here, point, is actually very important. We can have what seems to be a point of inflection, a point that's not a point, and we'll talk about that later. But it's a point on the graph of a function where the graph changes concavity. So it doesn't matter if the concavity is changing from concave up to concave down. So concave up to concave down, we get a point of inflection somewhere in there. Or concave down to concave up, we get a point of inflection somewhere in there. So if you think of my driving analogy, the point of inflection is where we go from turning to the left to turning to the right, or from turning to the right to turning to the left. So it's going to be any change in concavity. Now, I mentioned that it has to be a point on the graph. There are going to be times where a graph might change from concave down to concave up. To give you an example, we can look at the function 1 over x, and the function 1 over x is concave down to the left of x equals 0, and it's concave up to the right of x equals 0. However, at x equals 0, where the concavity changes from down to up, it's not a point of inflection because there's no point there. So we want to be careful that when we're analyzing concavity and we're specifically looking at points of inflection, the point of inflection actually has to be a point on the graph. So a theorem about point of inflections. So if a point is a point of inflection, then the second derivative either has to be 0 or the second derivative doesn't exist. What's actually going to happen if the second derivative doesn't exist is that the first derivative is not going to exist. So what we're going to see here is kind of the same sort of thing that we looked at with the first derivative, and where we're looking for relative extrema, where the first derivative changes from positive to negative. We were looking at what we called critical values. We're going to call these points where the second derivative is 0, or essentially the second derivative does not exist. I'm going to call those potential inflection points. We are not going to call them inflection points unless we know that the concavity actually changes. But we do know that if a point is an inflection point, the second derivative is either going to equal 0 or the second derivative does not exist. So just an add-on to that, the sign of the second derivative can only change where the second derivative is equal to 0 or where the second derivative does not exist. So these points right here, again, are what I'm going to call potential inflection points, or you might see me use the abbreviation PIP for short, potential inflection points. So if we're looking for inflection points, we're going to start with these potential inflection points where the derivative is equal to 0, or the second derivative is equal to 0, or the second derivative doesn't exist, and then analyze from there. So a couple of different questions that you might be asked. One is, where is a function concave up or concave down? In order to determine that, this is the process we're going to follow. We're going to take the second derivative. We're going to determine those potential inflection points. So where the second derivative is either equal to 0 or the second derivative doesn't exist. And then we're going to make a sign chart for the second derivative. If you remember when we started doing sign charts with the first derivative, I said it's really important that we label that sign chart so that we know what it's a sign chart for. So we might have a sign chart for the first derivative, which is going to indicate increasing and decreasing intervals on the function, or we might have a sign chart for a second derivative, which is going to indicate intervals of concave up and concave down. Once we have that sign chart, then we can make conclusions based on whether the second derivative is positive and negative on certain intervals. Specifically, if the second derivative is positive, then the function's concave up. If the second derivative is negative, then the function's concave down. The other type of question that might be asked is where we have points of inflection, and the process is going to be really similar. We're going to go through all the steps through making the sign chart, and then instead of looking for where the second derivative is positive or negative, we're going to be looking for where the second derivative changes from positive to negative or negative to positive, and then we want to eliminate any places where the function is undefined. So remember, an inflection point has to be a point on the graph. So if we have a change in concavity, but the function's not defined at that point, then it's not going to be a point of inflection.